All right, learners, welcome back. We're doing a deep dive today into something that's pretty exciting to me, at least. It's this research paper called Critical Tokens Matter, and it really gets into how LLMs reason, like how they think and solve problems.
Yeah, and I think what's so interesting about this research is they really try to get at why LLMs sometimes struggle with, things that involve reasoning,
Yeah.
especially like math problems.
Yeah, it's like when you're doing a math problem
Hmm.
and you just can't get the right answer, and then you go back and you realize, oh, shoot, I used a plus sign instead of a minus sign, and that one little thing just messed up the whole thing.
That's such a good analogy, and that's kind of what the researchers were looking at here. They found that LLMs can be really sensitive to like very specific pieces of information. They call these critical tokens.
Critical tokens. So what are those exactly? And how do they, mess up the LLM's reasoning?
Well, in LLMs, a token can be like a word or a number or even like a punctuation mark. It's just like the basic unit of information that the model processes. And what they found is that some of these tokens have like a really big impact on whether or not the LLM gets the right answer.
So it's not just the overall information the LLM is getting, but the specific words or symbols it sees along the way.
Exactly. And they actually show this in the paper. Like figure 2 has this word problem about like paying back debt.
Okay, I see it. It looks like the LLM's response changes a lot depending on if it focuses on the word owed or paid.
Yeah, exactly. When the LLM sees owed, it thinks the person still has to pay that amount, so it gets the calculation wrong. But when it sees paid, it understands that some of the debt's already gone.
Wow. So one little word owed or paid was like a switch that sends the LLM down the right path over the wrong one.
That's right. And the cool thing is the researchers actually measured how much of an impact these critical tokens have. Figure 1 shows this big difference in accuracy when they replace those critical tokens with other tokens.
It's like they found the LLM's weakness, you know, the places where it's most likely to make a mistake.
Yeah, that's a good way to think about it. And they didn't just notice this, they also figured out a way to find these critical tokens.
Oh, okay. How'd they do that? It seems like it would take forever to look at every single word the LLM processes.
Yeah, you're right, that would be a huge task. So instead, they came up with this clever technique called contrastive estimation. Think of it like comparing two different ways of looking at the same information.
Two different ways. What do you mean?
So like imagine you have two models. One is trained on, correct reasoning and the other is trained on incorrect reasoning. Contrastive estimation compares how likely each token is to be generated by these two
So
models.
if a token is way more likely to come from the model trained on the wrong reasoning, that's like a warning sign.
Exactly. That tells us that that token might be a critical token that's causing the LLM to make mistakes.
Okay, so they're using these two competing models to help them find the tokens that are causing trouble.
That's a good way to put it. And if you want to see what this looks like, check out figure 3 in the paper.
Yeah, I see it. It's almost like the two models are arguing, and the token that they disagree about the most is the critical one.
That's a good analogy. It shows how this technique can find those specific tokens that might lead to errors in reasoning.
So once they found these critical tokens, what did they do with that information?
That's where the really cool part comes in. They use this knowledge to make a new training algorithm called cDPO. It stands for Contrastive Direct Preference Optimization.
cDPO. Okay, that sounds a little complicated. Can you explain that in a simpler way?
Sure. Basically, cDPO uses those critical tokens to make the LLM better during training. It's kind of like giving the LLM a cheat sheet that highlights the words or symbols that it needs to pay extra attention to.
So instead of just learning from whether it got the answer right or wrong, the LLM is getting feedback on specific tokens that might have confused it.
Exactly. It's a more focused way of improving the LLM's reasoning skills.
That makes a lot of sense. So did this new training method actually work? Did cDPO actually make the LLM better?
That's the exciting part. They tried cDPO on two different data sets, GSM8K and MATH500, and with several different LLM models.
And it looks like from section 4 of the paper, the results were really good. They saw big improvements across the board. Seems like focusing on these critical tokens really made a difference.
Absolutely. It shows how important it is to understand these small but powerful parts of how LLMs reason.
This is all so fascinating. It's like we're getting a behind-the-scenes look at how these AI systems work.
It's a good reminder that even though LLMs can seem really smart, they're still machines that can be affected by these little things.
And by understanding those things, we can make them even better and more reliable.
That's right. And there's still so much more to learn in this area.
Well, before we get too far ahead of ourselves, let's look at how they actually use this cDPO training algorithm.
Good idea. Let's take a look at figure 4. It shows the main steps involved in their approach.
All right, figure 4 it is. Let's see what they did to make those LLMs learn better.
Okay, so figure 4 shows us the two main steps involved in using cDPO to train LLMs. The first step is all about gathering the right data to train those two models we talked about before. The one trained on correct reasoning and the one trained on incorrect reasoning.
Right, so they need to create those two different perspectives to help them find those critical tokens. But I think they mentioned something about being careful about the data they used.
Yeah, you're right. They didn't want to just use any random data to train the models. They specifically picked examples that showed both successful and unsuccessful reasoning so that the models could learn from a wider range of situations.
So they're not just showing the models what good reasoning looks like, but also all the different ways reasoning can go wrong.
Exactly. That way, the models can get a more complete picture of the reasoning process.
Makes sense. So once they have these well-trained models, how do they actually use them to make the main LLM better?
That's where step 2 comes in. In this step, they create something called a token-level preference dataset. It's basically a collection of examples where each token in the incorrect reasoning paths gets a score based on how much it contributed to the error.
So this is where they actually link those critical token scores to the training process.
Exactly. By giving scores to the individual tokens in those incorrect reasoning paths, they can see exactly where things went wrong.
And this is where the cDPO algorithm comes in, right?
Right. cDPO uses this token level scoring to adjust how the LLM learns. It basically penalizes the model for generating those critical tokens that are likely to cause errors.
So it's like the algorithm saying, hey, pay attention to these words. They're the ones messing you up.
Exactly. By pointing out those critical tokens during training cDPO helps the LLM avoid those mistakes and stay on the right track.
I'm starting to see how powerful this could be. It's like they're giving the LLM better judgment, helping it tell the difference between good and bad reasoning steps.
That's a good point. And they actually didn't just develop cDPO, they also compared it to other training methods to see how it measured up. They looked at standard DPO and another method called RPO, which adds something called a negative log likelihood term.
And how did cDPO do against the competition?
Well, the results are shown in Table 1, and it looks like cDPO consistently did better than the other methods. It had the best accuracy scores across both the GSM8K and MATH500 datasets.
Wow. So their approach really did make a big difference. It's amazing how much focusing on those critical tokens improved the LLM's reasoning skills. But did they do anything else to make sure that their contrastive estimation technique was actually working the way they thought it was?
You're feeling like a true scientist.
Right.
Yeah, they did go a step further to check if the tokens they identified as critical were really the cause of those reasoning errors. They did a special experiment to isolate the effects of these critical tokens.
Okay, I'm curious how they did that. What did this experiment look like?
They took a bunch of incorrect reasoning paths from the GSM8K dataset, and for each one, they found the token with the lowest score, meaning the one most likely to be a critical token.
So they were like looking for the main suspects that were causing the reasoning problems.
Right. Then they did something clever. They ran the LLM twice, once with the critical token still there, and once with the critical token replaced with a different token.
Like a controlled experiment to see if changing that one token really made a difference.
Exactly. And the results, which are in Figure 5, are pretty interesting. When they replaced that critical token, the accuracy scores got a lot better. So this proved that the critical token they found was a big part of why the LLM was making mistakes.
Like taking out a broken part from a machine, and suddenly everything works better.
That's a great way to put it. And they didn't just stop at comparing accuracy scores. They wanted to see how the different training methods like DPO, RPO, and cDPO actually affected how the LLM learned on a deeper level. So they looked at something called the log probabilities of chosen and rejected sequences during training.
So they were looking at how likely the LLM was to choose the right reasoning paths compared to the wrong ones.
Exactly. Figure 6 shows this really well. It shows that compared to the other methods, cDPO did a much better job of separating the chosen correct sequences from the rejected incorrect sequences.
So cDPO not only helped the LLM get more accurate answers, but also made its decision-making process more accurate.
Yeah, cDPO made it more likely that the LLM would create correct reasoning paths, and at the same time, it suppressed those critical tokens that were likely to cause errors.
Like cDPO is fine-tuning the way the LLM makes decisions, helping it be more careful and precise in its reasoning.
Exactly. And all of this comes from really understanding those critical tokens, those tiny but powerful elements that can make or break the whole reasoning process.
This research is really amazing. It's incredible how researchers are figuring out these little details about how LLMs work, and it's really making me think differently about how these AI systems process information.
It really shows how important it is to look at things on a really detailed level, like at the level of individual tokens, to understand and improve complex AI systems like LLMs. And speaking of details, the researchers didn't stop there. They wanted to go even deeper and refine their approach even more.
Oh, what else did they try?
Mm.
What else did they try?
So remember how they used those incorrect reasoning paths to train the models? Well, they thought, what if we're a little more picky about which incorrect paths we actually use?
Okay, so instead of using all the incorrect paths, they tried being more selective.
Exactly. They wanted to find like the best balance. They needed enough variety in the errors, but not so much that it overwhelmed the model with useless information. So they experimented with using like the top 25% or 50% or 75% of those incorrect paths.
It's kind of like finding the right amount of spices in a recipe, right? Too much of one thing can ruin the whole dish, but too little, and it's just bland.
That's a perfect analogy. And from what they found in Table 2, it looks like picking the top 50% of those incorrect paths actually worked the best for the GSM8K dataset.
Interesting. So finding that sweet spot is really important to make the most of their training data.
Yeah, exactly. It shows that you need to really think carefully about what data you use to train these models to make sure they learn as effectively as possible.
This whole paper's been a real eye-opener. It's amazing how researchers are digging into these tiny details of how LLMs learn and then using that knowledge to come up with these cool new techniques like cDPO.
It's like this constant back and forth, you know. They discover something new and then they use that to make things even better. And it's cool how they're getting ideas from all these different areas to make these breakthroughs.
Yeah, they mentioned contrastive decoding in the paper, which has been used to make generated text sound more natural and smooth. And they talked about connections to reinforcement learning algorithms, which have been really helpful in making LLMs do what humans want them to do.
Yeah, it's really interesting how all these different ideas are coming together and pushing this whole field forward so fast.
It feels like we're witnessing something truly groundbreaking. Well, I think that about wraps up our deep dive into critical tokens matter.
Yeah, we covered a lot of ground today.
We learned about how powerful these little words can be, the clever ways researchers are finding them, and the big performance improvements they're getting with methods like cDPO.
It's been a fascinating journey.
And like always, we encourage you to check out the research paper yourself and keep thinking about these ideas. There's still so much more to explore. Until next time, learners.